Well, how do we calculate equilibrium constants? The equilibrium constant will depend on the pressure, because rates of reaction depend on pressure. I'm sorry, did I say pressure? Temperature. Equilibrium constants depend on temperature. Rates occur differently at different temperatures. So we often specify the temperature when we calculate an equilibrium constant, but it doesn't show up as part of the equilibrium expression. Concentrations, when we measure a concentration for an equilibrium constant, it always needs to be in units of moles per liter volume. That's a convention, and we'll study moles per liter when we get to I think it's chapter 12. So we have moles per liter for all the concentrations, but then we drop the units in the equilibrium constant. So the equilibrium constant doesn't have any units. And if that bothers you, which, it bothers me, but there's an explanation of how that works, and I'll explain that if you'd like. So the concentrations will not always be the same for a given reaction, but the equilibrium constant will be the same at a particular temperature. So here's an example of calculating an equilibrium constant. So here's the chemical reaction, and we're given concentrations. This capital M is the abbreviation for moles per liter. So this is equal to 0.11 moles per liter. And we're not going to trick you on the units when it comes to doing these. But I just want you to know what those capital M's are. So the hydrogen concentration is 0.11 moles per liter. The iodine concentration is 0.11 moles per liter. The hydrogen iodide concentration is 0.78 moles per liter. And they're saying find the equilibrium constant. So these are the concentrations at equilibrium. So we write out our equilibrium expression. It's the product squared divided by this reactant and this reactant. So there's our expression. And then we're going to take these numbers and plug them into the expression and do the calculation. So it's 0.78 squared divided by 0.1 divided by 0.11, and it comes out to be 50. Any questions? I see some blank stares of concern at the screen and some open mouths, just silent. What? That's a good question. Where did this 0.78 come from? These were given to us. So someone did an experiment and they measured the concentrations. And they're saying, this was the concentration of this, and this was the concentration of that. That's data. So you don't come up with that, that's handed to you. That's another good question. Will they give you all of them? They will give you the ones that you need. In this reaction, they are all gases. If there was a solid or a liquid present, they wouldn't give it to you because you don't need it. And it's difficult to calculate a concentration of a solid or a liquid. It's kind of meaningless in a way. So to calculate KEQ, yes, we will give you all the concentrations. But what we'll also see is if we know what KEQ is, if we give you KEQ in all but one of these concentrations, we can solve for that also. Any other questions? So consider this reaction. There's the chemical equation. It says a mixture of carbon monoxide, hydrogen, and methanol is allowed to come to equilibrium at 225 degrees Celsius. The measured equilibrium concentrations are, and they list them out for you. What is the value of the equilibrium constant at this temperature? So they're asking us to calculate the equilibrium constant. So we start out by writing the expression KEQ equals what? We got the CH3OH on top, yeah, and divided by the CO and H2 squared. So you write that out. That's just from looking at this equation. There aren't any solids or liquids, so everything gets included. And now they gave us numbers for each of these, and so we just put them in. The CH3OH is 0.151. You know, it's always a good idea to make sure that these are in moles per liter, and they all are. And then this is one of those situations where you can just drop the units. So we should all be like, phew, we can ignore units for just a minute. So 0.151 divided by, the CO is 0.489, and the H2 is 0.146, getting smaller and smaller here, squared. Now, the next part of doing it on your calculator can be challenging for some students because your calculator speaks a slightly different language, doesn't it? So make sure, get your calculator out and do this with me. It really depends on what kind of a calculator you have. The problem that a lot of students are going to run into is that you've got numbers multiplied in the denominator. So I'm going to actually write out keystrokes here. 0.151 divided by 0.489 divided by 0.146 x squared equals. So 0.141 divided by 0.489 divided by 0.146 squared. This comes out to be 14.5. And it has no units. Now, if you're one of many people who look at this and say, you can't divide, that's multiplying. Okay? There are different ways to put this into your calculator, and you need to do the way that makes the most sense to you, because that's what you'll remember. So I'm going to show you another way to do this. You can do 0.151 divided by parentheses 0.489 times 0.146 x squared, parentheses, equals, and you will get the same number. Now, you're all supposed to have a scientific calculator, so you should have an x squared button. If you didn't have one, you could do 0.146 times 0.146 for this part, because that's what squared is. It's the number multiplied by itself twice. Any questions? So that was calculating equilibrium constants. How could we use equilibrium constants? Why do we have them in the first place? What good are they? Well, we can use an equilibrium constant to help us predict how much of a reactant or a product is present at equilibrium. So this is a very practical sort of problem. So, you know, maybe you are in the business of making fertilizer. Fertilizers, many of them are made through chemical reactions. And so you've got this big chemical reaction, and you know the equilibrium constant for your reaction, and you want to know how much of your product is going to be there. Okay, this is this is kind of adding a layer to stoichiometry. In stoichiometry, we were assuming that the reaction went all the way to completion. But it turns out a lot of chemical reactions don't. And so the equilibrium constant gives us information about, well, if I've got these concentrations of these, this quantity and this quantity, then what concentration of this will there be at equilibrium? So in this example, we're given the concentrations of all but one of the chemicals, and we're given the value of the equilibrium constant. Here, KEQ equals 2. And now they're saying find the missing concentration. So we start out the same by writing the equilibrium expression. It's the products divided by the reactants. This one has a coefficient of 2, so it gets squared here. And now what we want to do is we want to identify, well, what are we trying to find? Right? We're trying to find this guy. We need to rearrange the equation and solve for that guy. So in this example from your book, they did algebra magic, and they came up with this. If you want to see how to do the algebra magic, I would be happy to show you. This is one of those situations where you have fractions, and so like with the gas laws, I told you, let's cross multiply, get rid of the fractions, and then rearrange, and we should come up with this. So this tells us that the concentration of the CO2 equals the equilibrium constant times this over this. So then we know all these numbers, we put them in, and we run them through our calculator, and we come up with a carbon dioxide concentration of 1.10. This unit seems to have magically appeared, right? But in all of these calculations, the concentrations are in moles per liter, capital M, and so we just put that back when we're done. Any questions? Let's do an example. Iodine decomposes at high temperature to form iodine atoms. The reaction is a pretty simple one here. I2 is in equilibrium with 2 I atoms, and the equilibrium constant is 0.011 at 120 degrees Celsius. You're going to see a lot of temperatures thrown around here. The temperature is not used in a calculation. But because an equilibrium depends on the temperature, we specify the temperature because it's not going to be 0.011 at 25 degrees Celsius. It's going to be something else. Bless you. So in an equilibrium mixture, the concentration of I2 is 0.10, capital M. What's the equilibrium concentration of I? So what this part here is saying is that, don't do that. There we go. The concentration of I2 is equal to 0.10, capital M. And here we have KEQ. So we're finding the equilibrium concentration of the other substance. So KEQ is products over reactants. So it's I squared divided by I2. And we need to find out the concentration of I. So what I'm going to do first is I'm going to cross multiply to get rid of that fraction. Well, there's a fraction on this side. There's no fraction on that side. We can make that into a fraction over 1. So we're going to take the numerator of one side times the denominator of the other side. So I'm going to get KEQ times the concentration of I2 equals 1 times the concentration of I squared. Well, now I have an equation for I squared, right? How do I figure out what I is? Well, I need to take the square root. I squared, well, it's like x squared if I want to know what x is. Right, so if x squared equals 9, what's x? It's 3, right? It's the square root of 9. So this tells us that the concentration of I is the square root of KEQ times I2. So KEQ is 0.011 and I2 was 0.10, and the square root of that product. In some calculators, you have to put the square root in first, and some you have to put it in last. But I'm ending up with 0.033. And what unit should that concentration have? Capital M. Because for these calculations, the concentrations are always given in moles per liter, capital M. Any questions? Yes?
The very first example, you covered out a little bit, with scientific notation, and the other one was, I believe, just like 1 or 2. How do you know what we're rounding it to? Like, how?
Okay, that's a good question. How do you know how many digits to round this to? Rules of significant figures still apply. So here, the equilibrium constant has 2 significant figures, and the concentration has 2 significant figures, so I'm going to round my answer to 2. This is all multiplying and dividing, so whatever number has the fewest significant figures, that's how many will end up in your answer. Now, could this be expressed in scientific notation? Certainly. Could be 3.3 times 10 to the minus 2. And that's an equally correct answer. My rule of thumb is if you have to get your finger out and count zeros, put it in scientific notation and spare all of us the counting, right? I don't like doing that. I can't track more than about 3 zeros. Any other questions?